kind of, let's say, conductor and a galvanometer. And then Faraday's noticed when the switch is closed, a magnetic field is produced in the coil, and that current is really induced when we are closing the circuit. Then when we, like, this switch here is closed. And one thing that also he noticed, that if we are closing the switch, then the current is going to be detected by the galvanometer here in a certain direction. And when we are going to open the switch, we're going to have the current induced in the opposite direction. Then this is really something that was maybe, okay, what's going on? Because there is a change in the magnetic field, and we are going to see what is really causing that EMF. Now, EMF is induced in a coil when a bar magnet also is pushed in and out of it, and the EMFs are really reversed by reversing the poles. Here, if you look, I am bringing in the north pole towards a coil, then I'm going to have a current induced in this direction, which is the clockwise direction. If I'm bringing the north pole, it's going to be counterclockwise. Again, this is for the south. If I'm bringing the south, then the current is going to be counterclockwise, and if I am moving away, the south is going to be in the opposite direction. If that magnet is stationary, no motion, then there is no motion at all. There is no current at all. Now, we are going to also here talk later, maybe with more details. I don't know why I have the electric generator here, that it is a coil that is rotated in a magnetic field that is producing an alternating current. Alternating current, remember, we introduced that as being something like this. Then it is changing in magnitude and direction. Okay? And we're going to talk about these later. Now, what is magnetic flux? We defined magnetic flux last lecture. That is phi. It is BA times cosine theta. And remember, we said that A, it is a vector, the area here. This is the area. It is a vector that is perpendicular to the area itself. It's not in the same direction as the area. And then always when I am trying to calculate, the BA cosine, when I am creating, the flux, I am looking for BA cosine theta, and B, it is the magnetic field, and A, it is the area. Okay, and the area vector is perpendicular. Now, any change in the magnetic flux increases EMF. Okay, then it's here, any change is gonna make an EMF. We call this electromagnetic induction. The units for phi are Tesla times meters squared. And phi, in general, its magnitude, it is BA cosine phi. Now, we are going to talk about then the connection between Faraday's law and Lenz's law. We have like that EMF that can produce is directly proportional to the change in the flux. Okay, the change in the flux, and change in the flux is gonna be okay, then the EMF has to do with the change in flux. EMF greatest when delta T is short, which means you are doing this like change fast. EMF is proportional, inversely proportional to delta T, and also to the number of turns, it's directly proportional. Then apparently, according to Faraday's law of induction, EMF equals minus N, and its uppercase means the number of turns, phi, it is the flux, okay? And of course, T, it is the time, okay? And here, I'm not interested in the flux, I'm interested in the change in the flux. Now, I said in order to calculate the magnitude, this is the magnitude of the EMF. We use Faraday's law in order to calculate or find its direction. We use Lenz's law. The minus means that EMF creates a current I and magnetic field B that oppose the change in the flux delta phi. Which means here, I wanna maybe here say something more about it. I will say anytime you're gonna have something called B original and B induced. There are two fields. One of them original, okay, the one that is in the problem, and there is another one that is gonna be produced, induced, and it is produced and it is induced. If there is an increase in the original, then this one here, it should be decreased. Therefore, both in opposite direction. They're gonna come, one of them is in the opposite of the other. Now, if there is, for the original, there is a decrease, then B induced is gonna work to increase the flux. Therefore, they're gonna support each other. They're gonna be, they are going to be both in the same direction. I will use for that here, I'm gonna use here like B original and B induced. Here, this is maybe like, I wanna reflect that it's gonna be in the opposite direction. Then this is gonna be B induced. Now here, this is just to show you, we have here a coil and we have a current that is going through it that is in this direction, okay? And the bar magnet here is gonna be a thrust into the coil, means it's gonna be approaching. And when it is approaching with a north pole here, I will say this is gonna be original. And the strength of the magnetic field increases in the coil, and then the current induced in the coil is going to create another field that is going to be in the opposite direction. Then here, B induced should be in that direction. In the opposite direction of the bar magnets to oppose the increase. This is one aspect of Lenz's law. Induction opposes any change in flux. B and C are two other situations where here we have again the magnet is moving away. Then B original which is created by like here, B original is in this direction, but decreases. Therefore, the current in this coil is gonna be actually in the same direction. Then B induced. By the way, here we shouldn't have a battery at all. Okay. They are adding it just to show you that there is an induced, because this is as if it's showing you that there is an actual battery. There is no actual battery here. Okay. Then here B induced is gonna be in this direction, and therefore when I'm gonna use the right hand rule, okay, I'm gonna say that the magnetic field, it should be now in the same direction, and therefore the coil current is gonna be in this direction. Now the rule is, first ask, increase or decrease in the original B. And the decrease or increase can be indicated by bringing the magnet in, by closing a circuit, okay, by increasing the strength of the field. And then if increase, induced will be in the opposite direction. If there is a decrease in the original, induced will be in the same direction. And then you will use right hand rule to determine the direction of the magnetic field, of the current, sorry. Because you know the magnetic field, then you're gonna use the current rule. Now, to use Lenz's law to determine the directions of the induced magnetic fields, currents, and EMF, make a sketch of the situation for use in visualizing and recording directions. Determine the direction of the magnetic field. This one here, I will say the original. Determine whether the flux is increasing or decreasing. Now determine the direction of the induced magnetic field. It opposes the change in the flux, adding or subtracting from the original field. And then you are going to use the right hand rule to determine the direction of the induced current. And the direction or polarity of the induced EMF will now drive a current in this direction and can be represented as current emerging from the positive terminal. Yeah, this is what your textbook is doing, but I feel it confusing a little bit. Now, this is really here a question, just here to practice what is the value of the magnetic flux at coil 2 due to coil 1. Then we have two situations. This is one and this is the other one. Okay, coil 1 here, and it's if you look at coil 1 and this one, use the right hand rule, use your fingers to carry the current, you will find that the magnetic field at the center is gonna be out of the page, and it is 90 degrees with A. Then phi is gonna be BA cosine theta, and BA cosine 90 is gonna be 0. Because now for coil number 2, okay, you're gonna find that the magnetic field here is gonna be this way. This is from coil number 1. Then it is, we said out of the page, and we're gonna find that its area, it is here. Okay, then you're gonna find the angle between them is 90, and therefore is gonna be 0. For the second one here, That is a wire that this is for A. For B, this is a current that is going to be up, and therefore the magnetic field, if we use the thumb for I, then the magnetic field here it is crosses, and here it is dots. All right, and then here is gonna be across, is gonna be into the page here, and also we're gonna find that it's like the area for it is gonna be like this, and then therefore also theta equals 90, and then phi is gonna be 0, calculating the flux. Let's look at this one here. For this one here, referring to figure 2358, what are the directions of the currents in coils 1, 2, and 3? Assume that the coils are lying in the plane of the circuit. All right, then they are really in the plane of the circuit. When the switch is first closed. Okay, now when we switch when we have the switch first closed, then phi increases in the circuit, which means now the magnetic field from the original, we call this the original, is gonna be the magnetic flux increasing, and therefore the coil should have a current that is gonna working and tie to this, and therefore is gonna be having the magnetic field first. Okay, let me see. Okay, here for this I'm talking about number 1. Okay, the magnetic field is gonna be here going in and here going out. Okay, and therefore is going to be in this direction for the magnetic field, the original. Then this one is going to be original. Therefore, the induced should be this. Okay, which means it's out of the page. And then if you use the right-hand rule, you're going to find that the current should be in this direction in order to produce an induced current in this direction. Now for coil number 2, magnetic field from coil should be, then currents are shown right-hand rule counterclockwise. Okay, now for coil number 3, when we have the current going in this direction, again the B original is gonna be like this. Okay, and of course it should be here I'm using the red for the induced, and there is gonna be counterclockwise as well. Now for the one here, okay, the current is gonna create a magnetic field here, that this is gonna be cross, and here is gonna be dot entering. Okay, and again we should have its magnetic field, the induced one, outwards, and therefore is gonna be that coil. We're gonna have the magnetic field, the induced, out of the page, and therefore is gonna be the current is gonna be clockwise. Now the second one, it is when the switch has been closed for a long time, no change, and therefore no current. And now when the switch is open, it should be the opposite, then clockwise, clockwise, counterclockwise. What if the battery was reversed? Again, we're gonna have that clockwise, clockwise, counterclockwise. and no current. Of course, it has been closed for a while, and then also for the last part is gonna switch, okay, from clockwise to counterclockwise. This is another question. 0.25 meter radius, 510 coil is rotated 1/4 of a revolution in 4.71 millisecond, originally having its plane perpendicular to a uniform magnetic field. Then its plane was perpendicular to a uniform magnetic field, like this. Find the magnetic field strength needed to induce an average EMF of 10,000 volts. Then EMF equals N. Here I'm interested only in the magnitude, N delta phi over delta T, and that is NB delta A over delta T. And because B it is, phi, I mean, it is B times A. And therefore, we can find the magnetic field as EMF delta T over N delta A. And that is, remember the area, because it's a loop, it is pi r squared. And if you have any centimeters, you need to convert into meters. All right, I'm gonna stop here and continue to the second part.